Hello everyone, welcome to the webinar on Aromia bungii of the Group 2 EU Priority Pest. As you might know, since last year, we have provided 3 webinars on the EFSA Plants Pest Survey Methodological Framework and the toolkit, including the RIPEST and the OptiPest. 4 webinars of the Group 1 Fruit Flies Streptidae and 2 webinars of the Group 2 EU Priority Pests. If you did not attend the previous webinars and you would like to know more about them, the recorded presentations are available on EFSA's YouTube channel and on the EU Academy website. This is the third and the last webinar of a round of 3, and today's presentation will refer specifically to the pest Aromia bungii. Lastly, for the new attendees, and as a reminder, since the microphones are mute, the Q&A chat is enabled for you to ask any question that you might come up while the experts are presenting. Let me introduce you some housekeeping rules. You are automatically connected to the audio broadcast, one-way audio, listening only mode, you cannot speak. The event is in English. Questions should be submitted in English via the Q&A chat. If some questions remain unanswered, you can submit them via email. This event is being recorded, and recordings will be published on the EFSA's official YouTube channel and in the EU Academy. We will send all the information after the webinar. After this event, we will be requested to evaluate the EFSA's event filling out a Microsoft survey. As you can see in the screen, this is the agenda for today. So we are now in the introduction, and then I will give the floor to the 2 experts who will give us the presentation, and then we will get to the quiz, and there is where we will use the Mentimeter. And around 11, in 1 hour, we will finish this webinar. So, who we are? As you might know them from the previous webinar, today with us is Juan Navas. He's a member of EFSA's Pest Survey Methods Working Group and a research scientist at the Institute for Sustainable Agriculture for the Spanish National Research. And also with us is Alessandro Bianchi. He is the coordinator for surveillance and outbreak control of quarantine pests at the Plant Health Service in the Lombardy region. My name is Jose Ovejas, and I'm a journalist, and I will be the moderator of this webinar. So, as I said before, we are going to use the Mentimeter to know who is in the room. We would like to invite you all to participate in a poll to know who is in the room. Please proceed to search www.menti.com with your mobile phone or laptop. To participate, you can either use the QR code or enter the code that will be displayed in your screen in a few seconds and click the Join button. Before we begin with the poll, I would like to stress that Mentimeter will be also used at the end of the webinar to display several questions that the experts have prepared to check the understanding of the participants of the contents of this webinar. Therefore, it is advisable for you to keep this in mind and have an electronic device nearby to expedite the process. So, here's the first poll. As you can see in the top of the slide, you can see the code. If you're using www.menti.com, 37644364. I can see some of you are answering already. So as you can see, we can see the answers. Most of you are from the National Plant Protection Organization at central and regional level. We have also 18 persons at the moment from the super laboratory diagnostics, 12 from the risk manager involved in related decisions. It's important for you to know how to use Mentimeter, as I said, to use it at the end of the webinar for the quiz that the experts had prepared. Okay, so before the presentation, we would like to show you a short video regarding project activities.
This initiative provides technical and scientific support on plant pest surveillance for improving crisis preparedness in plant health. The European Food Safety Authority is the reference body for risk assessment of food and feed in the European Union, and its work covers the entire food chain, from field to fork. The target audience of this initiative is both in the 27 European member states and the third countries. The inspection services of national, regional, or local authorities competent for the planning and execution of the pest surveillance, the services that support the inspection with laboratory diagnostics, the risk managers that are involved in decisions related to the planning of surveillance activities, and manage the contingency plans for crisis preparedness in case of outbreaks of regulated pests. 3 webinars have already been provided. Webinar 1 on the Plant Pest Survey Methodological Framework, Webinar 2 on the Pest Survey Toolkit, RIPEST, Webinar 3 on the Multi-Pest Survey Optimization, OptiPest. The recordings are available in the EFSA official YouTube channel and in the EU Academy platform. Starting from March 2025, we are providing specific webinars for the preparation and design of detection surveys for the 20 EU priority pests that are listed in the annex of the Commission Delegated Regulation 1702 of 2019, and a specific e-learning course that will provide the participant with an overview of the methodology for preparing, designing, implementing and reporting of surveys of Union quarantine pests using the tools developed by EFSA. The e-learning course will be available online, and individual modules won't require the user's attention for more than 30 minutes. The course will be interactive and consider a good balance between theory and practical exercises, as well as a final certificate of attendance at the finalization of all modules. After participation, any attendant will be able to prepare, design, execute, and conclude the detection, delimiting and buffer zone surveys using the methodological framework and tools developed by EFSA. Send your application or contact us to receive more information to.
So now is the time to give the floor to our 2 experts. Juan, Alessandro, the floor is yours.
So good morning, everyone, and good morning, Juan.
So good morning, Alessandro. So and to everybody attending this webinar. So Alessandro, are you ready to start working on a survey design for Aromia?
Yes, I am. I thought we could begin by reviewing the biology and distribution of Aromia bungii and highlights the main differences compared to other longhorn beetles. Then perhaps you could walk us through how to apply the EFSA methodological framework for survey design. And finally, you could show us how RIPEST can be used in practice. So does that work for you?
Yes, sure. So, but let's first let's go to know about this pest a little bit better.
Yes, so this is our pest, Aromia bungii, or the redneck longhorn beetle. It has some distinctive traits that set it apart from other longhorn beetles, such as Anoplophora chinensis or Glabrypenis, which were discussed in earlier webinars. Most of the background information comes from the EFSA resources, including the pest survey card, accessible through the RIPEST app, the story map, and the pest reports that rank it among EU candidate priority pests. The EPO datasheet is also a key reference for its biology and regulatory context. Aromia bungii is native to East Asia, where it occurs in China, the Korean Peninsula, Mongolia, and Vietnam. In Japan, it was first reported in 2013. In Europe, it is present and currently under eradication or containment in Germany, in Bavaria, where it was first detected in 2011, And in Italy, with outbreaks reported in Campania in 2012, the following year in Lombardy, and more recently in Lazio and Tuscany. In all these areas, the pest remains localized and is subject to official control measure. The potential distribution of Aromia in the EU largely matches the area where its main hosts, prunus species, occur. Temperature has a strong effect on the life cycle, but overall, climate doesn't seem to limit its establishment in Europe. Given the wide presence of prunus plants, Aromia could potentially establish wherever these hosts are common, with the main exception being the far north of Sweden and Finland. Of course, local biotic and abiotic factors can still affect how suitable an area is. For example, infestation are often found in urban or peri-urban environments. Now, let's take a look at the EU regulatory framework. Aromia bungii is classified as a union quarantine pest and is also included among the 20 priority pests listed under Commission Delegated Regulation 1702 of 2019. This means that there are strict obligations in place, including annual surveys of the pest. According to Commission implementing decision on Aromia bungii, emergency measures have also been adopted to prevent both the introduction and the spread of the pest within the Union. Here we can see the life cycle, which usually lasts between 2 and 4 years, depending on temperature and the condition of the host. Adults emerge mainly from the late spring to summer, leaving those large oval exit holes on infested trees. After emerging, they feed on young twigs to complete their sexual maturation. Females lay their eggs under the bark, on the trunk or main branches. After about a week, the larvae hatch and they first feed beneath the bark and then bore deep into the wood, creating long galleries. This larval phase is the longest stage and it can last up to 3 years. Finally, pupation taking place inside the chamber within the wood, usually in spring. And then new adults soon emerge, starting the cycle again. So now let's focus on Aromia bungii host plants and the main sign of infestation. Both are key elements for a survey design. So Aromia is an Elugophagus species, mainly attacking prunus trees. In its native range, the main hosts are apricots, peach, plum, and cherry trees. In the field, the first visible sign is usually the accumulation of a reddish larval frass at the base of the trunk, together with oval exit holes about 12 millimeters wide. The frass is produced by larvae as they feed on a tunnel inside the woods. Its amount increases with larval age and infestation level. Although these signs are not unique to the redneck longor beetle, it may appear with other wood-boring beetles or moths. Anyway, they remain the most reliable fields indicator, as you can see in the pictures.
So, Alessandro, I have a question. So, based on this information, would you say that for a detection survey, we should focus on prunus species as the target host?
Yes, for a detection survey, it's recommended to focus exclusively on prunus species. In China, other trees have been reported as potential hosts, but those records are still unconfirmed.
Great. So I have one more question. So when we have different species present, Aromia species present in an area, how can we make sure that we are correctly identifying Aromia bungii?
Yes, starting from the signs on trees, Aromia bungii produces oval or slightly irregular exit holes, while, for example, Anoplophora species live perfectly round holes, as you can see in the pictures. In Europe, Anoplophora species are more polyphagous, attacking a broader range of trees such as maple, elm, poplar, and willow. Adults of redneck longur beetle are 2 to 4 centimeters long, with shiny black elytra and red prothorax, which clearly distinguishes them from native Aromia moscata, which is smaller and uniformly dark metallic, as you can see in the pictures. Larvae reach 40 to 50 millimeters and occur in 2 different types, A and B types. Morphological identification is possible, but molecular tests are always recommended when in doubt. For detailed and validated procedures, the EPO diagnostic standard remains the main reference.
So thanks, Alessandro, was very clear. So these traits are essential for correct identification during the survey. So thank you.
Yes. Now let's take a look at the damage caused by this pest. On trees, we can observe exit holes and extensive larval galleries in the wood of trunks and main branches. This can cause dieback and sometimes tree mortality. From an economic point of view, the pest is highly destructive in peach and apricot orchards, but can also damage plum and cherry trees. It may even affect wood production in wild cherry, as the internal galleries degrade the timber quality. From a social and environmental perspective, Aromia impacts ornamental prunus trees in urban areas, such as streets, parks, and gardens, and could reduce natural habitats characterized by prunus species. Another key aspect for designing a survey strategy is understanding the pathways of introduction. The main entry pathway into Europe is untreated wood packaging material, such as pellets, crates, and dunnage, especially from East Asia, where the pest is native. Eggs, larvae, or pupae may survive inside the wood until adult emergence, and occasionally adults may hitchhike in imported goods or packaging. Secondary pathways include the imports of infested plant material, particularly prunus plants for planting, which can host eggs or early larva stage under the bark.
So Alessandro, so related to this, how far can Aromia bungii spread in 1 year according to EFSA estimates?
Well, according to an expert knowledge elicitation carried out by EFSA, the maximum distance that Aromia is expected to spread in 1 year is around 309 meters. The uncertainty range is quite wide, from about 28 up to 1,220 meters, but overall this confirms that natural spread is relatively limited. So Juan, could you now give us a brief overview of the EFSA survey methodology?
Yes, please, next slide. Yeah, I will quickly go over a few key aspects of the EFSA statistical survey methodology. And the first step is to decide which type of survey we want to perform. So there are 3 different main types of pest freedom surveys: detection, delimiting, and buffer zone surveys, as you see on the slide. All of them share a common goal, so to provide evidence of pest freedom in the survey area. And the EFSA methodology, including the repest tool, can be applied to all of them, to all of the 3 survey types. So in a detection survey, we ask if the pest is present in the survey area. And these detection surveys are used when the pest has not been previously found in the survey area, or it is not known to occur in the survey area. So therefore, the aim is to prove pest freedom while also enabling the earliest possible detection of invasion. So next, the delimiting survey asks how far has it spread. The limiting surveys are performed once an infestation has already been detected, just to map the infected area where the pest is circulating. And finally, the buffer zone surveys ask how it spreads further, so are used to check whether the pest has spread beyond the infested area outside the demarcated area of the outbreak. So in this webinar for Aromia bungii, we will focus on detection surveys to substantiate pest freedom. Next slide, please. So, but why do we need this methodological framework for surveillance? Well, it's clear that because we cannot check every single plant with a perfect test. That is just impossible. So instead, we only survey part of the population and then draw conclusions for the rest of this population. So we can think in like an iceberg, so in which we only see the tip, but most of this iceberg is hidden. So the statistics help us to measure how confident we can be that the whole area in the pest-free is pest-free, even if we only check a small part of the population. Next, please. So the first thing we need to do is to structure our target population. For that, we have 4 different levels. At the highest level, we have the survey area. That is usually the whole of the whole member state or a part of a member state, depending on the particular case. Within the survey area, we have the epidemiological units. And within the epidemiological units, we might be able to define risk factors that tell us where the pest might be more likely to occur. And the lowest level is the inspection unit. That is what we inspect in the field and where we apply the detection method. Next, please. So after defining the survey area, the next level is the epidemiological unit, which is a subset of the survey area and is defined as a homogeneous area. In this area, the interaction between the pest, the host plants, and the environmental factors would result in the same epidemiology, meaning that all the hosts within the same epidemiological unit would have a similar probability of being infected by the pest. So at this point, Alessandro, what do you think, which epidemiological units we should consider for our pest today, Aromia bungii?
Yes, I would say that from Aromia bungii, we should focus on 3 main epidemiological units: orchards, urban areas, and natural areas. Prunus orchards are the most attractive and at-risk environments due to the high density of suitable hosts. Fruit plants are generally more attractive to the pest than ornamental trees. Urban areas, instead, are usually the first points of the introduction due to the ornamental trees, goods movements, and human activities that facilitate dispersal. Natural areas, although containing prunus species, only a small proportion, but can still carry a higher risk of spreading unnoticed, as the pest may remain hidden for long periods.
Yeah, yes, fully agree. So orchards let's say agricultural areas are the most attractive and risky areas. Urban areas are key points for introduction. And also natural areas are potential hidden reservoirs. So monitoring all of them is essential for early detection in detection surveys. Yes. So next slide. So now the next level is the inspection unit. That is the elementary unit on which the detection method is applied in the field. So this can be different units depending on the pest. But the important thing is that it define the size of the target population, meaning that the total number of inspection units is the size, or determine the size of our target population. Next, please. Next. So the inspection unit can vary from different pests and can be, for example, an individual tree or a group of trees, an individual fruit on the tree. In the case of an insect pest or vectors, it could be in the area that is covered by the trap or that we are using to detect the pest, or in some cases can be the pest directly. So, Alessandro, for Aromia bungii, what could be our inspection unit?
Yeah, well, for this pest, the inspection unit can be defined at two levels. Primarily, it's the single host tree, since that's where the infestation signs can be directly observed and recorded. However, when trapping is used, the inspection unit can also be considered as the area covered by a single trap, representing the area of potential beetle attraction and detection.
Okay, thanks. Great. Next slide. So concerning detection method that can be applied to detect this pest, we need to quantify the method sensitivity. So method sensitivity is defined as the probability to correctly identify the pest as being present if it is in the inspection unit. So it's important that involve a sequence of methods for detecting and identifying the pest from the field to the laboratory. So therefore, it depends on two components, the sampling effectiveness and the diagnostic sensitivity. So sampling effectiveness is the probability to capture the pest during an inspection, and if the pest is present in that inspection unit. The diagnostic sensitivity is a probability to detect the pest in the sample, given that the laboratory sample is truly positive. So, and therefore, method sensitivity is the multiplication of these two values, and is the probability to correctly capture and identify the pest in the inspection unit when it's present. So, which could be the detection and diagnostic method we can use for this pest? Alessandro.
Yes. In the field, infestation can be detected by the accumulation of larval frass, by the presence of exit holes, and by observing adults on the plant. Traps are also used in some countries to support the monitoring of the pest. However, since the signs are not so specific, confirmation requires sampling and morphological identification of adults or larvae, complemented when necessary by molecular analysis, especially for frost samples or immature and damaged specimens.
Yeah, great. Thanks, Alexandro. So it was very clear. So visual inspection remains the most practical approach, while molecular tools provide reliable confirmation in challenging cases particularly. So combining visual field inspection with morphological identification and molecular method clearly strengthens the detection and diagnosis. So, Alessandro, are there any capture traps that could be also available for Aromia bungii?
Yes, traps for redneck longhorn beetle are currently used on an experimental basis in some countries, including China, Japan, Italy, and Germany. They are generally cross-vein or black fly intercept panel traps, baited with a synthetic aggregation pheromone. Although the overall effectiveness is still uncertain, the results obtained so far are promising, and trapping is considered a useful complementary tool for monitoring adult population.
So we are progressing in the structure of the target population, and now we move to the risk factor. So a risk factor is any factor, either biotic or abiotic, that increase the probability of the pest being present in an area. So accounting for risk allows us to reduce the total sample size that we need to achieve the same design prevalence, let's say the level of pest freedom. Next. So in order to know where these areas of higher risk are located in our survey area, we should first know what the risk activity are for this pest that increase the chances of the pest to occur, and then identify the risk locations where this risk activity occur, and the areas of the risk areas are therefore the areas around the risk location that the pest may be found, usually calculated taking into account the spread capacity of the pest. Next. So in order to use a risk factor, we need to know the different levels associated with the risk factor. So usually high, medium, and the baseline, the proportion of the target population to which the risk levels apply, and the relative risk of each of the risk levels compared to the baseline risk. So, Alessandro, please, which risk factor could be used for Aromia?
Yes, the main risk factors for Aromia are closely linked to its introduction pathways. Survey should be pathway based, focusing on companies involved in the import, trade, or storage of high-risk materials. So the higher risk is associated with wood packaging material and wooden products of Prunus species, especially around import trades and storage sites and their surrounding areas. A secondary risk comes from the import of Prunus plants for planting, which makes nurseries, garden center, and nearby park or forest edges an important target areas for inspection.
Okay, so now we know the 4 levels to structure our target population, and we need to assign values to each survey parameter in order to be able to apply the statistical framework. So in this table, we list all the input that we require to run the RIPEST tool. Next, please. So the first is the target population. So as was discussed before, the inspection unit is Prunus. We will focus on Prunus species. So in this table, we show or summarize the estimated Prunus coverage across different land use categories, both for the European Union as a whole and for our reference territory that, as you see in the previous webinars, will be what we call Surveyland. So if we start with the European Union, that covers 423 million hectares in total. So from this, approximately 39.6 are classified as agricultural areas, 41% as natural areas, and around 4.4 as urban zones. But of them, about 0.92 are in particular from these land use types. The presence of Prunus species is relatively small, but is still significant, I think, because it's about 0.92 for agricultural areas, 0.5 for natural areas, and 2.3 urban for urban areas that are covered by Prunus. So according to these values and applying this the same percentage to the Surveyland, so we get this number of trees used that are calculated by multiplying the estimated area of Prunus for each land use in Surveyland by the estimated tree density then of Prunus in each of the areas, and then we estimate the total number of trees for each of that will be our epidemiological units agricultural, natural, and urban. And then we define the number of the size of our target population that is estimated in, next please. It's almost 197 million trees in Surveyland of prunus trees. Next. Then we move to the risk factors. So as was already explained by Alessandro, so Aromia spreads up to 309 meters per year. So this defines the risk level, the high risk level, and between 0 and 300 meters around the risk location. That, as was already mentioned, are entry points of import and trading of good packaging material. And the relative risk for this risk level 3 is 7.4, in compared with the risk level 1, that is the baseline, with a relative risk of 1. So the total number of potential entry points in Surveyland is estimated in about 3,250, but we consider that about 60% of them, so let's say 1,950, are entry points that imports prunus, that is our target cost. So that means that 0.32% of the target population, according to the numbers that are given in the table, are those on high risk level 3. And the remaining 99.68 are the rest of the target population, the baseline. Next, please. So now we have the inspection units, the size, number of inspection units, and the risk levels. So we need to know now the sampling effectiveness. So please, Alessandro, could you give us some information on this?
Yes, as mentioned before, we use the single host tree as the inspection units. The estimated sampling effectiveness is 44.6%, and is based on EFSA expert elicitation. This relatively moderate value reflects that the fact that the infestation signs are aspecific, making them difficult to detect or not yet producing visible external signs. The diagnostic sensitivity, when using morphological identification together with molecular analysis, is about 95%, ensuring a high level of reliability in confirming suspect samples. So these values are then used to calculate the overall survey sensitivity.
Thank you. So now we need to move to the next parameters, design prevalence and confidence level. So to set the, next please. So to set the design prevalence, that is a risk manager decision. So design prevalence is defined in the ISPN 31 as level of detection, and is defined as the maximum prevalence of the pest that can go undetected. Since, as was mentioned before, we can never survey the entire population, we cannot say with 100% certainty that the pest is not present in our area. So what we can say is the maximum prevalence that it could reach and still remain undetected. So in general, the lower the design prevalence, the more inspection units we need to reach the desired level of confidence. So in the graph in the slide, you can see in the x-axis the sample size, that is the number of inspection units we have to inspect, and the y-axis that shows the confidence level achieved. So for example, if we have 200 inspection units, the sample size, the confidence level is about 50% for a design prevalence of 0.5, but it increases to 75 for a design prevalence of 1%, and is close to 100% when we consider a design prevalence of 5%. So one way to think, practical way to think about the design prevalence could be what is the maximum pest prevalence that could still allow eradication in our particular case. But this will also obviously depends on the capacity of the pest and how effective could be the control measure we apply for the eradication. Next, please. So now we have all the parameters we need, and then we have the full characterization. Next, please. Of our target population with the 4 levels. So our survey area is Surveyland. Then as epidemiological units, we will use the land use categories as already described: agriculture or orchards, natural areas, and urban areas. The risk level is the import, storage, and trading of good packaging material, and the inspection unit in this case is a single host plant, a prunus tree. So then we move. I will share my screen, move to the Ripest tool. And then we will apply the Ripest tool to estimate the sample size for Aromia bungii according to the design I showed in the previous slide. So as you know, the Ripest tool guides you in the whole process from the initiation, preparation, design, implementation, and conclusion. So in this initiation phase, so we have to define the goal. What is the motivation of our survey? So in this example, we consider comply with the regulatory requirements. Our target pest is Aromia bungii, and the pest was not present in our area because we are dealing with a detection survey, and the pest was no other previous surveys were conducted before. Then we have to define the survey area, as was already explained, is the Surveyland, this invented country in the middle of nowhere. And we consider the whole territory, including all NAT1 levels. The host we will focus, as you know already, in prunus. So we don't have a save file, but of the host distribution, but it will not be important because it's not used for the calculations. Then in the preparation phase, this to survey is the next step, and we will describe the pest characteristic. So we can upload a save file of the environmental suitability, but it's optional and used not in the reporting, not for the calculation. So the target population, the inspection unit is the plant, single prunus tree. So now, still in the preparation phase for this inspection unit, the size of the target population is not infinite because we know the size. So we define 3 different EPI units, epidemiological units, agriculture, natural, and urban areas, and we include the number of inspection units according to the calculations we explained during the presentations. So we will apply risk factors in the survey, and yes, depends on the spread capacity of the pest. So this risk factor we label as entry points, but is related to the import, storage, and trading of good packaging material, and the risk locations of handling these materials, and the risk areas are defined as risk level 3 is an area of 28.7 hectares that is a band of radius of 300 meters from the location according to the spread capacity of the pest. Then we define the survey sites. We will focus on orchards, nurseries, forests, private gardens, public sites. The survey period is the optimum in which we can detect the pest from April till November. the detection method, as already explained by Alessandro, we will use visual examination. We will look for signs of the pest, and in particular in the trunk, the main branches, frost, presence of adults, etc., any sign of the pest in the tree. We collect branches, trunk, and pest if it's present. The sampling effectiveness is 44.6%. And for the laboratory detection method, we will use molecular method, in particular PCR and real-time PCR. And the diagnostic sensitivity for this laboratory method or detection method is 95%. So we can progress now in the design phase. We will use the standard values for the confidence level of 95% and a design prevalence of 1%. And then we have to indicate, as we are using risk factors, the relative risk and the percentage of the population that belongs to each of the risk levels for each of the AP units. As you remember, so this was estimated for the high risk level in 0.32%, and the remaining is the baseline. And we simulate, we obtain the sample size. So for independently of the AP units, we get a sample size of 17 for the high level and 121 for the baseline. So next, so is the allocation of the sample. We have the opportunity to reallocate. We will see later. And also to include the coordinate of the inspection unit is we have. So we can now finish, and we need to indicate if all the theoretical samples that we should take were the results, were taken and the results, and then we estimate the achieved confidence level that is the expected 95% when no detection was found. Then we can download the report, a standard report in PDF, but also importantly, as you know, those that attend the previous webinars, the Eurofield report. So, but then we have more options. We can go back to the design phase and decide to use convenience sampling. So in convenience samplings, we can decide so how much effort we can put in for the two risk levels we have. So we can decide, okay, as I consider that will be more likely to find the pest in those high-risk areas, so I will put 3 times more effort on these areas compared with the baseline, and then we re-estimate. So the sample size, as you can see, so this there is a more focus on a higher number of samples to be taken on the high-risk level compared to the baseline. So another option is if we want to reallocate, because our 3 AP units are very different in size on number of inspection units. So we can decide, okay, we will reallocate our samples according to these epidemiological units, because we're already proportional to the risk locations. And then we get, again, a different reallocation, and we get new sample sizes for each of the AP units and risk levels combinations. So to summarize, so can you see my screen, my presentation, sorry?
No.
Yeah. Sorry. Okay, could stop sharing.
Juan, yeah, I think you should stop sharing and share again. Yeah. I think, yeah, now we can see it.
And is in full screen?
Yes, it's in full screen.
Sorry. I'm confused now, sorry.
It's fine. Now we can see your presentation, but it's not in full screen.
No?
Yes, now it's correct.
Okay, sorry. So this table summarizes the different simulations, so we can compare in the upper part the estimated sample size by when we do not use risk factors. So we estimate more than 700 total sample size, but this in the table below we compare when we use the risk risk factor approach, and this is the one I presented. So then we reduce by 41% the sample size compared with when do not use risk factors, but very important, maintaining the theoretical achieved confidence level of 95%. Then when we use convenience sampling, so we still have a reduction that is about 80% compared with the, let's say, with the no risk simulation, and then similar values, but with different reallocation of the samples when we apply the convenience and reallocations of AP units. So this was all for concerning the trees as inspection unit. But as was already mentioned by Alessandro during the presentation, traps can be also used. Here you have the survey, the structure of the target population, but now considering the same levels except for the inspection unit that in this case is a trap that covers an area of 100 meters. And we have you will find all this information in the EU Academy, in which we repeat the same simulations for when using traps as an inspection unit. So that's all from my side. Thank you very much for your attention, and sorry for the mess with the screen. Sorry.
Thank you.
Okay, thank you both. Thank you, Juan. Thank you, Alessandro, for your presentation. Now is the time to do a small quiz to test yourself and see if you've understood the webinar. So for this, we need to use Mentimeter again. Please take your device and scan the QR code that you will see in a few seconds in your screen, or type www.menti.com on your browser and introduce the code that you will see again at the top of the slide. Let us share with you the Mentimeter. 1 second. Okay, so as you can see the QR code in your screen, you can scan it or either type www.menti.com and use the code that you can see in the top of the slide. It's 46542491. Okay, so the first question, which tree genus is considered the most susceptible to Aromia bungii? You can choose answer A, Prunus, option B, Pyrus, option C, Acer, option D, Punica. Okay, I see a lot of you are responding really fast. Okay, so most of you think the correct answer is the A, Prunus. Let's see what the expert think at the end of the test. So question 2, what is the primary pathway for the introduction of Aromia bungii into Europe? Option A, import of fruits. Option B, ornamental plant trade. Option C, movement of compost. Option D, wood packaging material. I give you some seconds to answer the question. Okay, so most of you think the correct answer is the option D, wood packaging material. Let's see at the end of the test. Question 3. What are the main signs to look for on host trees during detection surveys for Aromia bungii? Option A, exit holes and frost extraction. Option B, honeydew on leaves. Option C, webbing on branches. Option D, leaf mines. Okay, almost all of you might think the correct answer is the A. Let's see at the end of the test. Let's go for question 4. Why do we need a methodological framework for surveillance? Option A, to reduce the cost of pest control. Option B, to design statistically sound and risk-based surveys. Option C, to guarantee 100% pest exclusion. Option D, to replace field inspections. Okay, so let's move on to the last question. We will see the results after the test. So the fifth question is, which of the following is not a level of the target population? Option A, survey area. Option B, epidemiological unit. Option C, genetic unit. Option D, inspection unit. This is the last question, and after this, we will have the experts explaining the correct answers. Okay, so let's see the results. So Alexandra and Juan, you can now explain the correct answers.
Yeah, the most susceptible genus is obviously Prunus. The primary pathway for the introduction is wood packaging material, and the main signs to look for are the exit holes and frost extrusion.
Yeah, the question 4. So we need to design a statistically sound and risk-based surveys. We need a methodological framework, and the genetic unit is obviously not a level for the target population.
Okay, so thank you again. Thank you, Alessandro. Thank you, Juan, for your presentation. We are getting to the end. Thank you all for attending today. We are glad to see that today we reached more than 250 participants. In case we did not manage to answer all your questions, you will find them published on the EU Academy. Please note that similar questions will be grouped where possible. We will send specific information. The recordings of today's event will be available on EFSA's official YouTube channel and in the EU Academy with subtitles in 4 different languages: English, Spanish, French, and Arabic. Next webinar will take place in November 18th on Agrillus planipennis and on December 11th on Agrillus anxius. Before we leave, please take a few minutes to scan the QR code on the right side of the slide and fill in the evaluation survey. If you are unable to scan the QR code, after this event, you will receive a link to access the Microsoft survey form. Your feedback is essential to improve our future events. Thank you again for attending this webinar, and thank you once again, Juan and Alexander, for the presentation. We have now reached the end of the session. I hope you all have learned about this pest and are now well informed about it. This is the last webinar of a round of 3, and as I mentioned in the previous slide, the next webinar is scheduled for November 18th. I hope you all can attend. Have a great rest of the day.
Thank you. Bye.